Okay, if you were not here on Monday, we did move the exam to next Wednesday, right? So it is a week from today, all right? And I have also something else for you. It's not a quiz, though. Just take one of these and pass them there. I apologize. Real quick, I got to take this phone call. Yeah, no, oops. I meant to say the 11th. It's due, this is due on the day of the test. I mean, do y'all want to have it on the 12th? But you'd have to get it to me. You'd have to physically get it to the office. Yeah. Let's just make it the 11th. Please change that. Please change that due date to the 11th. This is take-home questions. Change the due date to the 11th, please. Okay, so I think it's pretty self-explanatory here. You're going to do all your work on separate paper. You're going to your work has to be neat and in order. So number 1 followed by number 2 followed by number 3. Okay. Staple all your work to this page with this page on top. So this is going to be your like cover sheet. And then you'll sign that little. You'll put your name in that first blank, and then you'll sign it on the bottom. That's just saying you're going to work alone on this. You're not going to go work in groups. You're not going to go to the tutoring lab and get help. You can use your book. You can use online resources, but you should work alone, okay? So if I just happen to stroll by the tutoring lab and I see people working on it, right, then there's a pretty severe penalty for working with other people on this, right? It's basically you're not going to be dropped from the course, you'll be failed in the course. So that's even worse. Yeah, so I have caught people before, yes. Yeah, it wasn't pretty. But I was more disappointed than anything else, you know, because I give instructions and they do it anyway. So, all right. Oh, do we want to talk about the problems? Those are all related rate problems. So the first one should look very familiar. We did one very, very similar to it. I do tell you that the volume of the sphere is decreasing, not increasing. That does factor in. And then number 2 is a rocket is launched vertically with a constant speed of 500 feet per second. How fast is it going? 500 feet per second. An observer on the ground is 1 mile away from the launch site. So a picture that would go with this would be, you have an observer, and we're going to neglect the height of the observer. We're just going to assume the observer is like a point on the ground, okay? You have a rocket that was launched, let's say from here. That rocket was launched, and here's the rocket, and it's shooting up, right? And it says that the distance between the person and the launch site is 1 mile. And at exactly the moment the rocket is 2 miles high, which would be somewhere up here, right? We want to know at that moment, right? Snapshot. What do we want to know? How fast is the angle of inclination changing? Angle of inclination is this angle right here. And I want that angle, I want that measurement in degrees per second. Did you get one of these? Did I not put enough down there? Who else needs one of these? Oops. on to, this is the take-home problems that are due on the 11th. I accidentally put the 12th on there. Please change that to the 11th. Oh, I'm sorry. And, okay. All right, so everyone kind of get an idea of what you're supposed to do in number 2? All right, number 3, I didn't do any problem like this. But there are some problems similar to this in the book. So you have a plane that's traveling north at 500 miles per hour that flies directly over San Antonio. So let's say this is San Antonio. We're looking from the top. This is San Antonio on the ground. You have this plane that flies north directly over San Antonio, 500 miles per hour. So there it goes, okay? And then 2 hours later, another plane flying east at 600 miles per hour flies over San Antonio. Okay, so there it goes, flying. And then an hour later, right, this plane is somewhere over here. Okay, so here's the plane, whatever. And the other plane is somewhere up here, right, because it's been traveling for a while now. Yes? And then I want to know how exactly 1 hour after this plane goes over San Antonio, how fast the distance between these two is changing. So if you had a rope tied between the two planes, like how fast is that rope coming out of your hand? No, I don't think so. Okay. All right. Well, it's not, you're freaking everyone out. It's not a Cal 3 problem.
It's not.
Yeah, it's not. Yeah. Okay. Good? Understand? The time in that problem matters, okay? The time, like 2 hours later and then an hour later, you have to factor all of that in to figure out what's going on. So think about it, do your best, and yeah. Questions? All right, so last class we did the mean value theorem. It's a very angry theorem, right? And today we're going to do 4.3, derivatives in shapes of graphs. And this section actually ties very well into the next section, which is, where the heck is it? Whoa, I went too far. For curve sketching. All right? So I'm going to, I kind of don't like the way the book does it, because the book, they kind of, in 4.3, they kind of show you one way of doing it, and then in 4.4, they kind of expand on it, and you have to kind of do things different in 4.4 than you do in 4.3. So I'm going to treat 4.3 as if we already know what's going to happen in 4.4. So I'm going to kind of present it to you with forward thinking, okay? We're going to think ahead a little bit. So just FYI. Also, in my experience with this whole idea of derivatives and shapes of graphs, when I was a student, all the textbooks and my professor presented it in a certain way that confused me. They use these things called sign charts or sign tables, and I didn't really understand it. So I do it just a little different. So if you go to a tutor or something and they're trying to help you and they're like trying to do this little sign chart, just understand it's going to be different than the way I presented it, or the way I'm going to present it to you. So just little asterisks next to everything I'm about to say. Okay, let's do this. So lots of notes in this section, but the whole idea here is this. Before graphing calculators, right? Before we had the technology that we have now, where I can just go to, the Google, or what's that thing I've been using, Desmos, and just type in a function, graph it, and have all this information. Before all that, we had to have ways, we as in human beings, had to have ways of trying to figure out what graphs looked like, right? And so you could almost say that this is somewhat obsolete, but the fundamental ideas behind it are important, all right? So how does the derivative of a function dictate the shape of the function? And that's what this is about. So we start off by going back to a college algebra concept of a function that is increasing, decreasing, or constant. So this is something from 1414 that you probably talked about. So a function is increasing means that as you look at the function and you read it almost like a book from left to right, that the function is going up, right? That's increasing. Decreasing would mean it's going to be going down, and then constant would mean that it's flat, right? Well, this first note says that if our derivative is positive on some interval AB, so the derivative being positive means that the slope of the tangent line is always pitched up like that a little bit. If the derivative is positive at every point inside of some interval, then the function must be increasing on that interval. It must be going up, right? Because all your tangent lines are positive. Now, if your derivative is negative on some interval, then the function is decreasing. And if the derivative is 0 on that interval, then it's constant, right? So that's what these say, and we can see this from this animation here, that this function is obviously increasing, right, as I read it from left to right. But if we look at the derivatives, notice the green line there is just representing the tangent line. All of those tangent lines are positive, no matter where I am here, right? So it's an increasing function. Decreasing, all those derivatives are negative, right? All these derivatives are negative. And then constant, of course, if we look at all those derivatives are all 0. So that's the visualization of what that note was saying. Pretty straightforward? Yeah. Okay. So let's take a look at a function that's a little more complicated. This one, it's not always increasing, right? Mm-hmm. It increases and then it decreases. So let's pull this back. Let's take a look. As we move from left to right, our function is increasing, our derivative is positive, right? We get to the top of this thing and our derivative is 0. Once we get past that little hump, now our derivative is negative, and then we get 0 again, and then our derivative is positive. So you see how the derivative the first derivative tells us a lot about the function already. It tells us where it's going to be going up and where it's going to be going down, where it may flatten out, right? So there's a lot of information in that derivative. So we're going to want to know when the derivative is positive. We're going to want to know when the derivative is negative, right? To be able to determine like where it goes up and down. So keep in mind, we're imagining that we have a function that we don't know what it looks like, and we're trying to figure out what it looks like. So we investigate the derivative to try and figure out this sort of thing, all right? So we have our first kind of major thing, which is called the first derivative test. It says, suppose C is a critical number of a continuous function. What does it mean to be a critical number? You have some point C that is a critical number of a function. What does it mean to be a critical number of a function?
Potential maximum.
It could be a maximum or minimum, could be, but there was a precise definition of what it meant to be a critical number. I'll give you a hint. One of two things have to happen at this value C. The derivative is either 0 or does not exist. Okay? Those are the two conditions. Well, you don't need both conditions. You need one of those conditions. So anywhere that your derivative is 0 or anywhere your derivative does not exist would qualify as a critical number. All right? So this says, suppose that C is a critical number. All right? Suppose you've got this place where the derivative doesn't exist or it's 0. Then, if the derivative changes from positive to negative at C, then f has a local maximum at C. So think about what that's saying. I have a graph, right? I have some value C where either the derivative is 0 or undefined. So let's take a look at what if it was 0. I know the slope of the tangent line there is 0, so it flattens out there, yes? Now it's saying, what if the derivative changes from positive to negative at C? That means to the left of C, my derivatives are positive, and to the right of C, my derivatives are negative. Then I had to go up and then down, right? If I have to go up and then down, then that has to be a local maximum, doesn't it? Make sense? Also, keep in mind, because someone might say, you know, look at this right here. What if you have a function here, c? What if that's a vertical asymptote and your function does this, and then on this side maybe it does this, and then they're like, hey, well that's not a local maximum. Well, look, c isn't even in the domain of the function. Okay, to be a critical number, you have to actually, that c has to be in the domain of the function.
It has to be continuous, right?
It would have to be continuous there. So it says of a continuous function.
Yeah.
So, but c must be in the domain of the function. All right, so that's why this can't happen. Understand? All right, so we're not even considering that. So this is what would happen if the derivative was 0. What if the derivative didn't exist? Can you give me an example of what happens, like where we have derivatives that don't exist?
Cusp or corner.
Cusp or corner. Good. So we have, let's say we have the derivative doesn't exist there, but it goes from increasing to decreasing. So the function would maybe look like this, and that would still be a local maximum, wouldn't it? It would still be the highest point in that little area, that little region, that little neighborhood. Yes? Okay, so that's what this is saying. If you go from positive to negative, add a critical number, then you've got a local maximum there, so long as that c is in the domain of the original function. Okay, if we change from negative to positive, it's the other way around, right? Negative to positive would look like this. It would have to be going down and then back up, right? And over here, we'll do it different. We'll do a corner like that. It would go down then up. So we have a local minimum, right? Now, what if it does not change? What if the sign of the derivative does not change? So if the derivative does not change at c, then f has no local maximum or minimum there. So it could look like, this last part would look like this. Let's say we have c. Let's say this is a critical number and that it flattens out. But it does not go from increasing to decreasing. It goes from, let's say, increasing to increasing, right? Then that's not going to be a local maximum or a minimum. Something better would be like this. I should have drawn that. So that doesn't look like the slope of the tangent line is 0. Let's do this. Okay, doesn't that look more like the slope of the tangent line? It was positive, right? And then it flattened out just for an instant. It was 0. And then right after that, it went back to being positive. This is not a local maximum. Tangent does that, right? The tangent function does something like that. Okay, so all of these are exactly what I just was showing you. Okay, so here, notice the derivative is positive, the negative. Up here, the derivative was 0. I can't get to it. It's all right. Just do that. Okay? So our derivative is 0 there. Here, our derivative is 0, but notice it went from decreasing to decreasing, so there was no change in sign there. It was negative, negative. The derivative was negative, negative. And then minimum went from negative derivative to positive derivative. We good? Okay. Now, that's what the first derivative tells us. The second derivative, we haven't even really ever talked about. I mean, we've taken second derivatives before, but we've never understood how they relate to the graph of a function. And they actually have a lot to do with what's happening with the look of a function. So concavity, we're going to talk about concavity inflection points in the second derivative concavity test. Okay, if a function f lies above all of its tangent lines on an interval I, then f is called concave up. What? If f lies below all of its tangent lines, then on an interval I, then f is called concave down. What? Okay, I'm not quite sure what that means, right? So let me draw you a function. All right, I'm going to draw a parabola. All right. Now I'm going to pick some random point here, and I'm going to draw its tangent line. Do you agree that the function, with the exception of that one point, the function is above this line? Mm-hmm. Yes? And wouldn't that work for any point I pick? If I pick this point, that function is above its tangent line. And then if I pick, any other point, the function is above the tangent line. Okay, if we ever get this to happen, This is called concave up. This is called concave up. It looks like a smile, doesn't it? Looks like a smile. So when you have a smiling looking function, we call that concave upward. Now concave downward is the opposite of that, like this. So if I pick a random point, notice that the graph is below the derivative, the graph of the line, the tangent line. So there's a tangent line. If I pick these tangent lines, no matter where I pick them, our graph is below. Does that make sense? Yeah. Okay. So this would be concave down, and it looks like a frown. So concave up is a smile, concave down is a frown. Got it? So what if we have something like this? It changes, doesn't it? Like here it looks like it's concave down, right? But then here it's concave up, and somewhere in there it switches, doesn't it? Like it looks like maybe right about here is where it makes a switch. Like here all your tangent lines are above, agreed? But then once you get to this point, all the tangent lines are below. So it was like concave down, and then concave up, and then you have this point at which it changes. And that point where it changes is what we're going to refer to as an inflection point. So it's kind of like you're frowning and then you're smiling. And where you actually had that mood change, right, that bipolar moment, is your inflection point. All right. So number three tells you, and this is the amazing part about the second derivative, it tells you how the second derivative is connected to concavity. If your second derivative, anywhere that your second derivative is positive, so if the second derivative is positive on some interval I, then f is concave up. If your second derivative is positive, it tells you where you're smiling. If your second derivative is negative, it tells you where you are frowning, where you're concave down. So quick recap. First derivative positive tells you where you're going up. First derivative negative tells you where you're going down. Second derivative positive tells you where you look like a smile. Second derivative negative tells you where you look like a frown. Got it? Sure? Okay, a point on a curve is called an inflection point if the function is continuous at that point and the sign of the second derivative changes at that point. So if you go from concave up to concave down, right? If you change from concave up to concave down, that point that you make that change is called the inflection point. Or if you go from concave down to concave up, same thing. As long as it changes from positive to negative or negative to positive, we call that an inflection point. So here's the concavity here. Okay, so over here, take a look at this. We are talking about the second derivative right now. The first derivative, we are increasing, right? But that's not what we're looking at here. Here, the second derivative is what? Negative, because the graph lies below the tangent line. But more importantly, it looks like a frown here, doesn't it? So it's going to look like a frown, and then we're going to have a switch right about there. You see it switched over? And now you are concave up. You are still concave up. What's going to happen here? Switch to concave down. Where's the next switch going to happen? Right there. Yep, we go back to concave up, and we remain concave up. You'll see that? So concavity has nothing to do with up, down. It has to do with frown, smile. Yes? Second derivative. So we have now what's called the second derivative test. This is a really cool test. It says, suppose that the second derivative is continuous near C. So that means that when we take the second derivative, it's defined and doesn't have any domain issues. We can take second derivatives, right? Okay. Then if the first derivative is zero at C, and the second derivative is positive, then we're looking at a local minimum. Let's see why. Okay, let's see why. This is a very cool test. Okay, we have some points C. If the first derivative is 0 there, that means that I know that the slope of the tangent line is flat. Yes? Now, what if the second derivative is positive there?
Concave up.
You're concave up. And the only way I can be concave up here is if it looked like a little smile. And if it looks like a smile there and the tangent line is 0 there, then it has to be a local minimum. Make sense? That's what this test is saying. This is basically the same thing but flipped over. So what if you have the derivative is 0, but the second derivative is negative? That means you're concave down, you look like a frown, and now you have a local maximum. So this is a really cool test because all you have to do is figure out what critical numbers you have, figure out where it's 0, and then take your second derivative and test your second derivative at that point. And if it comes out to be positive, you've got what, local min, and if it comes out to be negative, you got local max. So I basically do that here. Here's a point. Here's the first derivative is 0. Here's second derivative is positive. And that means your function had a local minimum there. Make sense? Okay. All right, that's it. That's what this section is about. So now what we're going to do is we're going to do some examples. All right, let's do it. Maybe. Now the thing about curve sketching is that we didn't really need all this stuff when we were graphing quadratics and polynomials so much. We need it for more advanced functions that are things that we don't normally deal with. So you're going to notice when I put these functions up here that you're not going to know what they look like without a calculator, without a computer. You're just going to not know what you've never really seen these before. So let's take a look at this function. Why don't we start out? Yeah, let's just start out with something that we may have seen before. Let's go with x over x squared plus 9. Now that is something that you would have seen potentially in college algebra. That is a rational function. So you know it's a polynomial divided by a polynomial, and then you have this big long procedure to graph it. What I'd like for us to do right now is I'd like for us to do this. Find where f is that. You see that little arrow? That's my notation. The book doesn't use that notation. What do you think I mean by that? Where f is not positive, increasing. Okay? I want to know where f is increasing. Keep in mind, so we don't lose sight of things here, if I have a function that does this, okay, if I wanted to know where a function was positive, that would mean anywhere where the graph was above the x-axis. That's what it means to say where the function is positive. This is not saying where the function is positive. This is saying where the function is increasing, right? That means where the derivative is positive. Yes? There's a difference. Okay. This would be where the function is negative, but that's not what we're looking at. All right? So I want to find that. I want to find where the function is going down, decreasing. I want to find any local maxes or mins, okay? If there's any local maximums or minimums, we're going to need to find them, all right? We're going to find where the function is doing this. What do you think I mean by that? Concave up. And we will also find where the function is going and doing that, which is concave down. And then finally, we're going to find any inflection points. Okay, so lots of things to do here. What are we going to need to do to figure out where it's going up and down? Take the first derivative, right? What are we going to need to do to find where it's concave up and down? Second derivative. So why don't we just get the derivatives out of the way right now? Okay, let's just take the first and second derivative so we have them, ready to go when we need them. So my first derivative of this function is going to be quotient rule. So derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared, which is, let's see, x squared plus 9 minus 2x squared over x squared plus 9 squared, which is 9 minus x squared over x squared plus 9 squared. Okay, so that's just applying the quotient rule, cleaning up the numerator, combining things together, and canceling or putting like terms together, and we should get that. Everyone agree? That's our first derivative. Okay, let's just box that up. We'll need that in a moment. We're going to need the second derivative also. So for my second derivative, I'm going to take the derivative of the derivative. So I'm going to do this derivative. Quotient rule again, right? What is the derivative of the top? Negative 2x times the bottom, x squared plus 9, quantity squared, minus, now be very careful here, what is the derivative of the bottom? It's a chain rule, right? Because the bottom is this squared, right? So when you take its derivative, the 2 has to come out. And then you reduce the power, so x squared plus 9 to the first power. Then, and take derivative of what's in here, which is 2x, and then times the top, right, which is 9 minus x squared. And if it looks bad, it's because it is. All right? Okay, so that's our derivative. Any questions on the derivative? Now, in the past, when we took derivatives of things, I said, really on the test, I really want the raw derivative. I'm going to be looking for the raw derivative. But later, you will have to be able to clean this up, right? What? Am I missing something?
The bottom square.
Oh, I did, yes. Thank you. Thank you. That's a 4. I'm not sure what you're seeing there. It's kind of blurry, I think. That was blurry. There we go. Okay, thank you. All right, so now we have to actually clean this thing up, all right? Because we're going to have to figure out where this is positive and negative, and we have to figure out where this is positive and negative. That's what we have to do, right? So we better make it look better before we do that. Oh man, what can I do? Let's look at that numerator, because there is something in that numerator that I can do. Notice we have this big chunk, right, times this big chunk right here. They both have some things in common. Like this has a negative 2x. This has a negative 2x, or I could say this one, right? I can pull out a negative 2x. I can also pull out an x squared plus 9. I have 2 factors here and a single factor here. So why don't I pull that out? I'm going to pull negative 2x out. I'm going to pull x squared plus 9 out. And then I'm going to put brackets, even though I could use parentheses. That's just to stress the fact that I'm doing a GCF out of the greatest common factor out of the top. So if I pull this out of here, what am I left with in here? Just x squared plus 9. I don't necessarily need parentheses around it. But if I multiply this times this, I would get back this. Agreed? I'll put parentheses there. This times this, I get back that. Now, I did pull this negative, didn't I?
Yes.
So it's going to be plus and I pulled a 2x out, but I still have a 2, so 2. I pulled the x squared plus 9 out, but I still have the 9 minus x squared. And that's all over x squared plus 9 to the 4th power. Y'all still with me? All right, now let's clean up the inside of this. And I'm going to try and save myself some time here. This right here is x squared plus 9 minus, or no, not minus, plus 18 minus 2x squared. So I just dropped the parentheses here, distributed a 2 through, and this is what I would get, right? And now I'll combine like terms, and that'll be my next line. Yes? I'm also going to do this. Right? That was those were both common factors. So I can cancel one of them out. So what I'm left with is negative 2x. And then what was in the bracket when I put it all together? We get negative x squared plus 27, right? I'm going to do it this way. 27 minus x squared. Same thing, right? That's what this is. And then on the bottom, x squared plus 9 cubed. There's my second derivative. So yes, you're going to have to be doing some algebra now. Questions? That was just because I need that to do all this now, right? So let's start figuring out how we're going to do this. And I think what I'll do is I'll write these derivatives down here next to it. The derivative was 9 minus x squared over x squared plus 9 squared. That was f prime, and then f double prime was negative 2x, and then 27 minus x squared over x squared plus 9 cubed. There's my second derivative, and then my first function. Okay, so there's all my information that I'm going to need. All right, so if I want to know where the derivative is positive and where it is negative, what I'm going to do is something that you may remember doing in the past, you may not. And it's like if you want to know where something is positive and negative, what you do is you actually first figure out where it's 0. All right, so I'm going to do these two pieces, I'm going to take my first derivative and set it to 0. All right, so I'm going to take f prime right now and set it equal to 0. So if I set f prime to 0, I take, 9 minus x squared over x squared plus 9 squared, set it to 0. And I talked about this in the past, that if you ever have a fraction equal to 0, you only have to look at the numerator. So this means that all we have to do is figure out where 9 minus x squared is 0. And that has two solutions of positive and negative 3. Right, so our first derivative is 0 at these two numbers. Now, we also have to look at something else. Where the first derivative does not exist, or where it's undefined. So basically, this first step right here is really saying to do what? Find the critical numbers. Now, the reason I need to do this, the first derivative does not exist is because we could have a corner or a cusp, which could give us a local max or min also. So I have to consider it. Now, does this first derivative ever not exist? Do you ever get division by 0? Is there any number that you can square, add 9 to it, and get 0? No, unless you're doing imaginary numbers, which we're not. So that's not possible. Other than that, there's no roots, there's no other domain issues. Agreed? So there's none here, okay? No critical numbers where the first derivative is undefined or anything like that. Okay, we good? All right. The next step is, see if this looks familiar to you at all. We're going to draw a number line, and we're going to plot our critical numbers. -3 and +3. I know right now that at 3 and -3, my first derivative is 0. But I'm really interested in knowing where it's positive and negative. So what I do is I use the -3 and the 3 to partition my number line into 3 regions. And what I'm going to do now is I'm going to pick test points. So some of this sounds familiar, okay? This test point idea. Plug in any 3 numbers you want, so long as they live in those regions. So any number you want to the left of -3. -4, okay, great. I'm going to notice that when I picked my test points, I put little X's here. I suggest you put X's and not dots because you might confuse that later with part of your graph, because we're going to be graphing this later. I also circle my test points as opposed to my critical numbers so I can distinguish them. Okay, so I have a test point of -4. What's a good test point in here? 0. And then a good test point here. 4. Okay. Could I have picked -100? Yes. Could I have picked 1/2? Yes. Could I have picked 10? Yes. It's up to you. All right? Now what I'm going to do next is I'm going to take these points and I'm going to plug them into the derivative. Why? Because what am I interested in? I want to know where the derivative is going, or I want to know where the derivative is positive, right? This happens when the derivative is positive. This happens when the derivative is negative, right? So if I want to know where the function's going up, I need to figure out where the derivative is positive. If I want to know where it's going down, I need to know where it's negative. I know that here and here it's 0. So what's happening to the left of -3? Well, plug that in to the derivative, see what happens. So I now need to test. I need to do f prime of -4. I need to do f prime of 0. I need to do f prime of 4. Normally I would have listed these vertically, but because of space, I'm just putting them sideways. So what happens when I plug -4 into the derivative? And where's my derivative? Right here? Let's plug -4 in here. What happens when I square -4? 16, and then I subtract it. So I get 9 minus 16, yes? Over, who cares? It's squared, right? Because that means it's positive on the bottom. So I have a negative over a positive,
Yeah.
which means it's negative,
Negative.
right? So watch what I put here. F down, right? See this right here, f of -4 turned out to be a negative number, which means the original function is going down over here. Now I plug 0 into the derivative. 0 into here, 9, that's positive. On the bottom, something squared, positive, positive over positive is positive, right? So I know that this is equal to a positive number. And that means my original function here is going up. And then I do the same thing with 4. If I plug in 4, I'm going to actually get the same thing that happened when I plugged in -4.
Yeah.
Okay, so it's going to turn out to be negative, which means my original function is going down. So are we going to be able to now answer where it's going up, where it's going down? Do you know of any local maximums or minimums? Look at the picture. Your graph is going down and then back up, right? Down and then back up. And the derivative is 0 here, isn't it? And then it's going up and then it's going down. And the derivative is 0 at 3. So this is going to be a local min, and this is going to be where we have a local max. Can you see it from our picture? Okay. All right, so we are going to be able to answer the first 3. All right, check, check, check. Let's go ahead and answer them right now. So how do I want the answers? Well, here's how we should write the answer. So I'll put colons next to these so you can put the answers in here. All right, so where is it going up? Just between -3 and 3, right? Between here and here. Don't mess with your test points. Your test points were only there to help you get the up and down. Between -3 and 3, the function's going up. So I say -3 to 3. And you can use open intervals like with the parentheses, or you can use brackets, but I suggest you always just use the parentheses, no matter what, because it is technically correct to have parentheses. Even if your function is defined at -3, you don't need the bracket. And there's a reason why. It has to do with the fact that to talk about increasing and decreasing, you need 2 points. Because it either goes up or down. You need 2 points to talk about that. So if you need 2 points, then a single point is not relevant. I don't know if that makes sense. There's an infinite number of points in here. So if you leave off one endpoint, it's okay. Yes?
At like -3.1 or something, is it possible that it's still going down?
At -3.1, which would be on this side. -2.9?
Yeah, -2.9.
Is it possible that it's still going? No.
No.
Nope. The function has to be going up there. That means, yeah, that's what's so profound about this. If you give me any 2 points over there, -2.9999, let's take that one, and let's take the other point, -2.99998, right? Those would be really close to one another. Then if I plug this in, I'm going to get an answer. If I plug this one in, that answer is going to be a little bit above it. It's got to be going up here. For all points in between here, we're going to go up. The function will rise. Okay? Where's the function going down? Well, to the left of 3, right? Sorry, to the left of -3? How far to the left of -3? Forever, right? Because if it ever did anything else, we would have been able to get that in our derivative. We would have had another solution, another point here, and we would have tested. So we are guaranteed that to the left of -3, this function was always going down. So that means I'm going to write -infinity to -3. Now that's not the only place it goes down. Also goes down to the right of 3. So I put the union symbol here, and then I say 3 to infinity. So I'm using a very loose interval notation here. I know some of you have seen like x is an element of, and you don't need to do that. It's okay. I understand what you're doing here. Everyone clear with those two answers? That's it. Now, find any local maximums or minimums. So do we have a local max? Where? Local maximum is here, isn't it? Up, then down. If our derivative went from positive to negative. So I have a local max, f of 3, right? If we plug 3 into the function, we should figure out what, that will tell us what the maximum value is. So let's plug 3 into the original function. We get 3 over, let's see, 9 plus 9, 3 over 18? 3 over 18? So that's what? 1/6? 1/6. And then if we plug in -3, that's where we have a local minimum, isn't it? So plug -3 into this, and we get almost the same answer, -1/6. All right, how do y'all feel about that? Okay, this problem is taking a while, isn't it? Okay, we have 3 more things to answer. Questions? How do you think we're going to go about doing the next 3? Questions? We're going to do the exact same process for the second derivative. So we're going to take the second derivative, we're going to figure out where it's 0. We're going to take the second derivative, we're going to figure out where it's undefined. We're going to draw a number line, we're going to partition our number line, we're going to pick test points, we're going to plug those test points into the second derivative. That's going to tell us concave up, concave down. Then we're going to answer the questions. So we're repeating the same thing with the second derivative. So where is my second derivative? 0. Okay, so I look at my very ugly second derivative, and I set it equal to 0. And we already learned that when you do that, you just have to set the top to 0, right? Yeah. Okay, and, well, set this to 0 and set that to 0, right? If I set this to 0, I just get 0. So x is 0 is one answer. And then, if I set this to 0, I'll have to move the x squared over, take square root of both sides, do plus or minus. So I'm going to have plus or minus root 27, which is some number, right? Root 27, whatever it is. Who cares? I'm not going to get a decimal. I'm just going to leave it. Now, any place where the second derivative does not exist? Yeah, because look, the only problem we could possibly have is division by 0. And again, same argument, that can never be 0. If that was x squared minus 9, we'd have problems, but it's x squared plus 9, so we're okay. So nope, none here. And now I go to a number line. Now on this number line, I'm going to plot all 3 of these points. See, it's important that you remember that you're going to get plus or minus here when you take the square root on both sides, because if you forget that it's plus or minus, you only get one of these answers. One of those, you won't have that one. So be careful there. This is going to create a natural partition of my number line into 4 regions, right? Which means I will have 4 test points. Anything that I want over here, anything I want over here, anything I want over here, and anything I want over here. So maybe it would be a good idea to have an understanding of what root 27 is. Well, what is it? What's bigger than this? What's something over here? What's that? 5 point something. So root 27, like root 36 would be bigger than this, right? And root 36 is 6. So I can pick 6. If you want, just get your calculator out and figure out what that is as a decimal and just pick any number bigger than it. But without a calculator, I can probably reason it out that I could pick 6. So to be safe, how about I go with 10? All right, I'll just be super safe. 10. How about in here? Pi, yes, you could do pi. Pi would work. 1? Let's go with 1. Here, -1. And over here, how about we go with -10? All right, all of these have to be plugged into second derivative. So I'm going to do f double prime of -10. I'm going to do f double prime of -1. I'm going to do f double prime of 1. I'm going to do f double prime of 10. All right, here we go. See if we can't do this let's try and do this without actually plugging it in, because all we care about is whether or not it's positive or negative, right? That's all we care about. So let's try -10 right here. Second derivative. -2 times -10 would give me positive 20, right? So I'm going to say top left corner is positive times, what happens if I plug -10 in here? So -10 squared is 100. I'm taking 27, subtracting 100. That's going to give me a negative number. And then over, what can you tell me about the bottom? It's positive, because look, x squared plus 9, that's positive. Cubed, still positive. So isn't the denominator going to be positive all the time in all of these?
Yeah.
Okay, so the numerator here is negative. Negative over positive is negative. So I have a negative there, don't I? So you don't need the actual numerical value. You just need to know if it's positive or negative. So I know that the second derivative is negative here. That means in this region, the function is frowning, right? Concave down. You can one way you can remember it is negative people frown and positive people smile, right? That's not always the case, but. All right, let's plug in -1. Plug in -1 right there. It's going to be positive. And then another positive, and we already said that we're going to have positive on the bottom, right? So when we plug -1 in right there, we're going to get a positive. So this is positive, which means that our original function is concave up. What happens when we plug in 1? You get negative here, positive here. and over a positive. So we're going to, oh, I'm in the wrong one. Sorry. This one. Negative, positive, over positive, which is negative. And the last one, I think we get negative, 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 which is going to be positive. Okay, so F will be going down here, and F will be going up. And, you know, normally at this point, someone in the class asks the question of, you know, yeah, so exactly. If I get the first one, then can I just kind of know that the rest are just going to alternate? And the answer is no. You have to test each one because there are functions where you don't have a change. It does not change.
Yeah.
We haven't done one of those yet.
Like when it goes to 0 and then keeps going?
Yeah, like the tangent function does it. But there are other ones that would act that way. So you have to test them all. Sorry. All right. Okay, we're ready to answer the last three questions. Where is the function going up? Or sorry, concave up. Here and here, right? So between, how do I write this? Negative root 27 to 0, right? Concave up. And then also from root 27 on. So union root 27 to infinity. Follow me? Negative root 27 to 0, unioned 27 to infinity. And then when it's going down, it's to the left of root 27, and then between 0 and root 27. Wait, did I say root 20? To the left of negative root 27, and between 0 and root 27 is where it's concave down. So negative infinity to negative root 27, union 0 to root 27. Do we have any inflection points? That's anywhere that we have a change in concavity. And that's all of these critical numbers actually turn out to be inflection points. All of them. So with the inflection points, it's okay if you just list out the x values. You don't have to do f of, because we don't really need to know the height, like the max and min. Max and min is important because we want to know like the highest and lowest points of a graph. Inflection points are not as important that we know the height. So I'm just going to put here x is negative root 27, 0, and root 27. Yeah, those are our inflection points. All right, that only took, I don't know when we started, but it seems like that took about 30 minutes, 25 minutes or so. So what happens if you mess up the first derivative? It's all over, right? Because then your second derivative is wrong, and then everything else is wrong after that. Yeah, so there's a lot of room for error here. Oh, should we take a look at it? Yeah, let's take a look at it. Let's graph it real quick. Now, if you were to take what you learned in college algebra and combine it with what we just did, you would have a badass graph of this function. Because in college algebra, if you were asked to graph this, you would find the x-intercepts, which means you would set the numerator equal to 0, and we would have an x-intercept at 0. You would find the y-intercepts, which you would plug 0 in, and it's the same point. Then you would find any vertical and horizontal asymptotes. And you would have a horizontal asymptote like this. So you know that your graph would flatten out. And then you would have to do some test points. And you would figure in college algebra, you would have like this much. And you would try and draw a decent graph. What we have now that's even better than this is that we know that at 3 and negative 3, we have some stuff happening. So what did we have at negative 3? It was a local... It was a local min at negative 1/6. I'm gonna exaggerate my y-axis. So like, it was a local min at negative 3. Yes. Okay, and then at 3 it was a local max. Yes. So that was 1/6. This is negative 1/6.